Hello. Thank you, Mr. Luminet, for joining Danny and me today for a brief conversation to explore, let's say, a topic that is uniquely yours: black holes in the broadest sense. Mr. Jean-Pierre Luminet, Emeritus Research Director at the CNRS Astrophysics Laboratory of Marseille, thank you for being with us. Could you please introduce yourself to us?
Yes, of course. First of all, I fully share your project of making science accessible to the general public, as this has always been a central concern of mine, alongside my work as a researcher. Among countless books, I've published more than 30 works on general culture, what I would call scientific culture. And I've given countless lectures because I believe it is very important that knowledge which is truly surprising, very strange, and sometimes a bit mysterious be shared with a broad audience. Today, science plays a fundamental role, and understanding it properly is crucial. As for my background, briefly, I'm French, with a Provençal accent. I studied mathematics at the University of Marseille in the south of France until I happened to discover, reading some well-chosen literature, the mystery and magic of two great 20th century theories: general relativity and quantum physics. That's what led me to shift my focus to research in theoretical astrophysics and theoretical physics. So, in the mid-1970s, I went to Paris to write my doctoral thesis under one of the leading experts in black hole physics, Brandon Carter, who came from the renowned Cambridge School, alongside Roger Penrose, Stephen Hawking, and so on. So, I wrote my first thesis. It wasn't about black holes, but rather on a topic that was very relevant at the time, and still is today, though in a different light. We might get a chance to talk about it. It's about what we call singularities, space-time singularities, and in particular singularities cosmology. These are strange points in space and time where all physical quantities become infinite, and they raise a number of problems. Should they be part of physical theories, or should they be eliminated by refining those theories? So, in 1977, I defended my thesis on that topic, and in 1978, Brandon Carter made me a remarkable proposal about black holes. He knew I was interested in these objects, which already had a fairly solid theoretical foundation at the time, thanks to the work done by the Cambridge School and later the American School in Princeton, particularly through the efforts of John Wheeler and several other scientists, but they didn't have much of an experimental base in astrophysics. And his idea came from knowing that I was not only deeply interested in the subject itself, but also fascinated by the visual side of such phenomena. So, he said something along the lines of, "Draw me a black hole." What did that mean? Draw me a black hole. It meant creating the first digital simulation, something that had never been done, of what a black hole would actually look like. Not, of course, an isolated black hole by itself, black on black, nothing to see. But naturally, the idea was that the black hole is surrounded by a luminous structure. For example, what we call an accretion disk, a disk of hot gas. The challenge was that this had never been done before, so, of course, I was interested. It also gave me the opportunity to visualize something that is normally impossible to see, the black hole itself, the very symbol of astronomical invisibility. But once it's surrounded by matter, it appears framed in light. The equations of general relativity allow for extremely precise calculations on a computer after first writing out the equations, which unfortunately can't be solved analytically. That's why we use extensive computational modeling to account for all the phenomena predicted by general relativity. In other words, the curvature of space-time, that is, the bending of light rays and the distortion of images. And, of course, a black hole surrounded by a disk, a ring of matter, looks nothing like the planet Saturn with its rings. It appears as something extremely distorted. Even back then, people had begun talking about black holes in popular science realm. Today, they're everywhere, and we often see artistic renderings that are frankly inaccurate. What you usually see is a black sphere surrounded by a swirling ring, and that completely fails to reflect the true properties of spacetime. That was exactly the work I did, and I think we'll have the chance to come back to it in more detail. But for now, I'll keep it brief. I completed that work in just a few weeks, and then I published it in 1978 and 1979 as a paper. It explored how stars that pass very close to giant, supermassive black holes found at the centers of galaxies could be destroyed by what we call tidal gravitational forces of a black hole. That was purely theoretical work, long before any kind of observation was possible. At the time, I calculated and simulated how a star, during an initial pass near the black hole within a critical zone I had defined, would first be compressed into the plane of its orbit and ultimately explode. So I wrote a whole series of articles with astrophysical predictions. In French, I called them crêpes flambées stellaires, flambéed stellar pancakes, because these stars were flattened like pancakes and eventually gave off powerful bursts of radiation. And sure enough, about 10 years later, starting in the 1990s, these phenomena were actually observed, once we had access to X-ray observations thanks to space telescopes. These are highly energetic phenomena occurring in the cores of distant galaxies, which some interpret as the destruction of stars by tidal forces. And then there's another very important part of my work. I shifted scale, while of course continuing to follow all research related to black holes, and moved toward the cosmological scale, developing a whole series of models concerning the shape of space. In fact, I realized, this was in the early 1990s, that standard cosmology, relativistic cosmology, and the Big Bang models overlooked one possibility. That's because it isn't included in Einstein's theory itself. General relativity doesn't account for it. The possibility of defining the global shape of space. General relativity describes only the local properties of space, its curvature and so on, but not its overall shape. For example, it doesn't say whether space is finite or infinite. Both are compatible with the equations. So it becomes necessary to introduce mathematical assumptions, specifically those coming from a branch of mathematics known as topology. This field that was extensively developed in the 20th century by pure mathematicians, but that hadn't been incorporated into cosmological models. Given my interest in mathematics and geometry, I felt it was important to address that. And so, starting in the 1990s, I began developing what is now known as cosmic topology, creating an entire set of models of possible space models with strange and varied shapes, each with specific topological properties. What's interesting is that we can construct, at least theoretically, models of space that, again, are fully compatible with general relativity, but that completely distort our perception. Here we're dealing with a new kind of optical illusion. It's no longer a gravitational mirage caused by a compact object or a black hole. It's a global mirage, one that could lead us, based on the paths of light rays, to believe that the shape of space is different from what it actually is. We can construct models within the universe, in which space turns out to be much smaller than we might assume, because of a kind of image multiplication effect. So yes, it's true that I really enjoyed this line of work, because at the beginning it was not exactly orthodox, but I've always liked research that's a little, of course, not entirely outside standard models, but that brings in ideas that haven't yet been included. So it's true that for about 10 years this subject, which was initially very technical and highly mathematical, you had to study the properties of space with very strange shapes, wasn't taken very seriously by much of the cosmological community. That changed in 2003 when we received data from an American satellite WMAP, which observed with great precision the structure of what's known as the relic radiation or the cosmic microwave background, and identified some of its properties. There were some anomalies in relation to the strictly standard model, which described space as essentially infinite and without any specific topology. Together with my team, I interpreted these anomalies. One possible explanation we proposed was a very specific shape of space, known as the Poincaré dodecahedral space. It actually made the cover of Nature magazine in 2003. And from that point on, the field completely changed scale. It wasn't proof, just an indication with possibility of experimental confirmation. But after that, the topic experienced tremendous growth over at least the next 15 years. That's it. So it was done. That was my main contributions. And then starting in the 2000, around 2015 in particular, after I returned to the south of France, I turned my attention to various theories of quantum gravity, which, as you know, is one of the major areas of investigation in theoretical physics, or more broadly, in fundamental physics. This is one of the great topics of the 21st century. How can we reconcile general relativity with quantum physics? We'll have a chance to come back to it when we talk about black holes and the information paradox. So, the result of all this was a book I published titled L'écume de l'espace-temps, The Foam of Space-Time. It's not a technical book, but it contains about 100 equations. The most that can reasonably be said about all these approaches to quantum gravity, which, contrary to what we often read, are by no means limited to string theory or possibly loop quantum gravity. There are at least 7 different approaches, each more surprising than the last and each exploring a new path. None of them has fully developed yet, and this really is one of the major questions of our time. To develop a theory of quantum gravity that would resolve some of the problems in the standard models, such as the information paradox, which we'll also discuss, and quite possibly the issue of singularities, which are not very acceptable from a physical point of view. The question is, can we eliminate them within a quantum theory of gravity?
You mentioned that at the beginning of your career, you were the first to model the image of a black hole. Could you share what was perhaps the most challenging part of that process, particularly during the actual execution of the model? And as a follow-up, how well does that model align with the new insights we're now gaining from modern telescopes? In other words, what were the challenges in creating that first visualization? And what features of it have since been confirmed or newly revealed by recent observations?
To be honest, I didn't face any scientific difficulties while carrying out this calculation because it was enough just to write it down properly to formulate the problem correctly. After all, that's how research is done, isn't it? You simply write it down. The key is to correctly define the geometry of the problem. In other words, to imagine a black hole surrounded by a luminous structure, an accretion disk, to envision a kind of virtual photographic plate positioned at a certain distance, at a specific angle relative to the plane of the disk. Then to integrate the paths of light rays emitted from every point on the disk and determine how they would strike that photographic plate. That's how it was done. So, it was necessary to turn to the laws of light propagation in curved spacetime, and so on. It only took me a few weeks to properly formulate the equations. And really, there was nothing particularly difficult about it. And then what was perhaps most interesting were the limitations, specifically the technical limitations of that time. Once the equations were written down, there was of course no analytical solution, so they had to be solved numerically on a computer. At the time, we had a large transistor-based IBM computer at the Paris Observatory. This was before the era of personal computers. We wrote our programs in Fortran using punch cards, so that wasn't a major problem either. What was amusing looking back is that the computer would output tables of numbers, approximate values of the light flux we were getting on the photographic plate. But that didn't allow us to produce even close to a realistic image, and that's exactly what I wanted to achieve. We didn't have any software for that. All we had were tables of numbers. In other words, I had the light flux curves output by the computer, and I had to somehow transfer them onto a plate. So I made a large paper printout of this flux curve, which essentially represented my photographic plate, showing the photon density per unit area. And I drew it by hand. I overlaid a sheet of transparent paper, divided it into squares, and manually placed black dots. Well, actually, no. The density of the dots per unit area was proportional to the flux values given by the calculation. All in all, I finished the whole thing over 2 evenings. I drew around 10,000 black dots with a density proportional to the light flux. In other words, I took what was originally a negative and turned it into a positive image and published it. So it was a black and white image, because in fact it was what we call a bolometric image. That is, it represented an integration over all possible and conceivable wavelengths. It wasn't a radio image, or an optical one, or anything like that, so there was no actual color to work with. In any case, even today, when we use color in such images, we still use false colors. And so, I had the opportunity to create this model, which at the time seemed natural to me. It didn't seem extraordinary in any way. Then, in 2019, the Event Horizon Telescope presented the first telescopic image, including a supplementary view, of the presumed supermassive black hole at the center of galaxy M87, surrounded by a glowing corona, which was interpreted as an accretion disk with hotspots, and so on. Yes, and the second part of the question concerns both the difficulty and the similarity with the images from 2000 and 2019. First of all, you may recall that at the end of my 1979 paper, in the final sentence, I wrote that this was, of course, a theoretical calculation, and that if someday we were able to obtain such an image through observation, it would necessarily imply a high resolution or sharp visual acuity, which at the time was unimaginable. And I also mentioned that the ideal object would be a supermassive black hole, the existence of which had just begun to be suspected at the very center of the galaxy M87. I never imagined this could happen within my lifetime, let alone that M87 would actually be the first. Why? Simply because M87 contains a supermassive black hole whose mass is 5 to 6 billion times that of the Sun. And in terms of its apparent size in the sky, it is the largest, or rather the least small in the sky. Its projection on the sky is roughly equivalent to the size of a €1 coin placed on the surface of the Moon. At the time, I didn't yet know that radio wave observations made it possible to perform what's known as interferometry. That is, to link radio telescopes located in different parts of the world and use them in a mode called Very Long Baseline Interferometry, VLBI, effectively creating the equivalent of a single radio telescope the size of the entire network. And it was only much later that I learned that already in the 2000s, dozens of researchers from around the world, some of whom had been partly inspired by my 1978 to 1979 paper, began to ask a bold question: could a global network be created which they named the Event Horizon Telescope? The event horizon is the technical term for the surface of a black hole, to achieve extremely high resolution in the radio band at a precisely defined wavelength. The goal: to reach the capability to observe something as small as a coin placed on the surface of the moon while observing it from Earth. There were only two black holes suitable for this kind of observation: Messier 87, and the other is the black hole believed to be at the center of our own galaxy. Although when I wrote my article, this second one wasn't yet being discussed. The idea of observing it only emerged in the 1990s. It's much less massive, but also much closer. And those two factors balance each other out. So in terms of its apparent size against the background of the sky, it ends up occupying roughly the same angular size. The Event Horizon Telescope was created specifically to observe these two black holes. They were finally observed in 2017. So the first image, after numerical simulations and extremely complex data analysis, showed the black hole in Messier 87. And 2 years later, since it was somewhat more complex, an image was also obtained of the galactic black hole Sagittarius A star. So now we have two reconstructions. It's important to note that when we talk about telescope images, listeners or viewers might picture something like the beautiful photographs captured by the James Webb Space Telescope. But in this case, we're dealing with extremely complex reconstructions based on massive amounts of data. We're talking about petabytes of information collected by each radio telescope in the network data that must be integrated using advanced computational algorithms. There are several possible image reconstructions, and these are compared with theoretical models, like the ones I created 40 years ago, but now far more sophisticated, with many more parameters and powered by supercomputers. What we ultimately get is the so-called photograph of a black hole, which in reality isn't a true photograph at all but a reconstruction. And in conclusion, I won't go on too long, but regarding this match, indeed when we first saw those images I said, yes, we've reached the Lumines calculations. This is incredible, and so on. And it's true that at that moment I thought to myself, yes, that glowing ring with a bright spot, that's the Doppler effect, the very one I had calculated. It was astonishing. But then, as time went on, I began to ask myself more and more questions. Then other researchers began to wonder, is it really the accretion disk that we're seeing today? And while I haven't published a technical paper on this, I did write a post on my blog explaining that what we're seeing is not in fact the full accretion disk as I calculated it back in 1978. Rather, it's a finer and somewhat mysterious structure known as the photon ring. The photon ring is essentially a sequence, a cluster of secondary, tertiary, and even higher order images. When a black hole is surrounded by some structure, we see what's called the primary image, the direct view of the light rays. Even if they aren't heavily distorted, there is still some image distortion. It's still a direct image. But there are also light rays coming from the other side and curving back toward you, giving a much more distorted picture, which we call a secondary image, and so on, a tertiary image, etc. In short, higher order images of 2 and above. In fact, all these higher order images compress around what is called the black hole's shadow. In other words, they represent increasingly warped images of the event horizon itself, slightly magnified by gravitational lensing. What we see is a small glowing halo known as the photon ring. Ultimately, and this is something rarely discussed, at least in popular science literature, what we actually see in the telescope images produced by the Event Horizon Telescope is the photon ring. Aside from the article I wrote on the subject, it's almost never mentioned, or appears only briefly in a few technical papers. What we are seeing is not the full accretion disk, which in any case is very faint at the wavelengths being observed. On the other hand, what we're actually seeing is the photon ring. And more importantly, since we know the distance to these black holes and their masses, general relativity allows us to predict the size of the photon ring associated with a black hole of a given mass. And indeed, that predicted size matches exactly the average diameter of the glowing coronas seen in the images. But in reality, the photon ring is extremely thin and very fine. In the images of Messier 87 and Sagittarius A star, we see what look like crowns, but that's simply because the resolution isn't high enough, and so the photon ring's disk appears slightly thickened. In fact, the latest advances by the Event Horizon Telescope, made possible by new, more sophisticated software, are beginning to further sharpen the image, and what we see perfectly still corresponds to what we call the photon ring. That is the current state of black hole imaging today.
Thank you very much, Mr. Luminet. Thank you for these insights. As you mentioned earlier, you are also one of the pioneers in the theoretical study of tidal disruption events, or TDEs. Could you tell us a little more about this topic? Where do we currently stand in our understanding of this phenomenon? Are we still dealing solely with mathematical models? Or is this now something that astronomers are observing more frequently? What exactly happens? What do we actually observe? And are tidal disruption events always associated with black holes?
Yes. So, in order for objects like stars to be torn apart, extremely powerful tidal forces are required, forces that can, in fact, only be produced by black holes. That said, the strength and effects of a black hole's tidal field vary greatly depending on the black hole's mass. Around each black hole, we can define what's called the tidal radius, a critical distance. If a celestial object, say a planet or a star, in other words, something with a typical density of a few grams per cubic centimeter, crosses within this distance, it will be subjected to such intense gravitational stresses that it will be destroyed. This tidal radius is actually larger than the physical size of the black hole itself. At one point, I became interested in studying the interaction between black holes which masses are up to 100 million times less than the mass of the Sun and nearby stars, where certain variations occur. Once we had a grasp on that, the next step was to plug these values into the equations. And from an astrophysical standpoint, that's much more complex than calculating a black hole image because you have to take hydrodynamics into account. You need to model everything, including the structure of the star itself, as it enters the external tidal field, with compressive and expansive gravitational forces acting upon it, and so on. You have to track the dynamics because it's not a static configuration. And then you need to incorporate all of that into the equations. But before doing the calculations, it's always important to have a sense of geometric intuition. I didn't say, but when I was working on reproducing the image of a black hole, I already had an idea of what I should get, because I had that intuition about the geometry. And the same goes for stellar pancakes. A simple geometric reasoning led me to realize that tidal forces compress in a specific direction, so naturally the star would be flattened. And then I thought, if it's flattened more and more, extremely so, there must come a point when it can't be compressed any further, because the pressure, the temperature would rise dramatically and the whole thing might explode. Perhaps this would even trigger thermonuclear reactions inside the star because it's being heated to tens of millions of degrees. That's precisely why I modeled what I called flambéed stellar pancakes. So in our numerical simulations, we had to include nuclear physics, meaning a network of nuclear elements that would react based on temperature. We needed to see what would happen. It turned out to be quite complex. I worked on it through a series of research papers with different collaborators, and I made several predictions based on those studies. And as I mentioned earlier, starting in the 1990s, we began to observe events that were interpreted as tidal disruption events, or TDEs. In this series of papers, I showed my colleagues that there are significant differences between a star that merely approaches the critical distance, the tidal radius, and a star that actually crosses that threshold and is effectively destroyed. But what does it do? It doesn't explode. It gets torn apart, releasing gas. That is, it breaks up into smaller fragments and eventually dissociates. It loses its gravitational cohesion. It sheds some of its gas. In the end, roughly half of the gas released by the star remains in orbit around the black hole, while the other half is ejected into space. These early phases are statistically the most common in tidal disruption events, which scientists began observing more regularly starting in the 1990s. However, the most original part of the work I did was when we explored the case in which a star doesn't just skim the tidal radius, it actually plunges deeper into it. We looked at stars that penetrated 2, 3, even 4 times deeper than the critical tidal distance, and in some cases, up to 10 times deeper. And all this without necessarily falling directly into the black hole. In that regime, tidal forces become dramatically more intense. Unlike the inverse square law we usually associate with gravitational force, tidal forces scale with the inverse cube of the distance. So as the star approaches, the effects intensify violently. That's why we predicted that a star plunging significantly, say 5, 6, even 10 times deeper than the tidal radius, would suffer a much more brutal fate. We're talking about extreme compression, what I coined as flambéed stellar pancakes, followed by thermonuclear explosions and other dramatic processes. But it wasn't until the 2000s that astronomers began to observe events, usually in the distant cores of galaxies, that could be interpreted as these violent types of tidal disruption events. So yes, I started working on this in the 1980s, and at that time, I was one of the true pioneers in the field. I was also the first to carry out precise numerical simulations. Of course, since then, the field has evolved with much more sophisticated approaches. But for me, what matters most is launching new research directions, and then I moved to other questions. So later on, this research was expanded in a more sophisticated way, meaning with massive hydrodynamic numerical simulation that incorporated a great number of additional variables to obtain roughly the same results we had reached earlier, but with much more detailed modeling, allowing for closer comparisons with astronomical observations made in the past. As a result, nowadays we have a formal catalog. All these events are now known as TDEs, tidal disruption events. Today, TDEs encompass a wide range of phenomena. Some TDEs are relatively calm, where a star is stretched and torn apart. We now even have telescope images of such occurrences. But there are also much more violent cases. Outbursts of radiation so extreme they can't be explained by supernova explosions. These can only be accounted for by tidal detonations of stars, which I had actually predicted back in the 1980s. Nowadays, we have a catalog, accessible online, much like the gravitational wave event catalogs, and it lists around 100 documented TDEs observed over the past 2 decades. And the number is steadily growing as our telescopes become increasingly powerful.
Very good. Excellent. Thank you for the information about the tidal effect and observations of it. So, in 1977, as you told us, you defended a dissertation on singularity in cosmology in Paris. How did that come about? Has science advanced in understanding singularity since then? Would you say that some things have truly moved forward in this area since that time?
Yes. This line of research, this dissertation topic came to me because singularities at that time considered exclusively within the framework of purely classical general relativity. Let's call it classical in the sense of non-quantum. And a few years earlier, the famous theorems known as the singularity theorems had been introduced, demonstrated by Roger Penrose and Stephen Hawking. These theorems mathematically showed, based on the equations of general relativity and a few quite plausible hypotheses about the nature of energy and a whole set of other things, that during what we call gravitational collapse, an event horizon is automatically formed. That is, a surface of no return. And beyond that, by extrapolating, we may end up at a singularity, a point in space-time where everything is, where curvature becomes infinite, and so on. By the way, this also applies to gravitational collapse leading to a black hole. So we had mathematical theorems demonstrating the inevitability of singularities in general relativity. I carried out that work, and at the time we asked ourselves, might these singularities be the result of overly simplified assumptions that can be made about the symmetries of space-time? So I wrote a dissertation on this topic in which I studied possible space-time models that were not realistic, but were technically and geometrically possible, in which, by removing symmetries, we examined whether singularities still persist when the symmetries are significantly reduced. And it turned out that yes, they do remain. So this aligned perfectly with the general a priori proof by Penrose and Stephen Hawking. That's it. That was the topic of my dissertation. How has this subject developed since then? Well, even back then it already posed a problem, because even though singularities were predicted as an inevitability by general relativity, for physicists, they were somewhat unacceptable. They sort of indicate a limitation of theory. Yes, they are elegant, they work well, but none of them are perfect. There exists a theory of gravity that is slightly different from general relativity, still classical in the sense that it includes no quantum phenomena at all. It's called Cartan's theory, which, by the way, Einstein himself was also interested in. In this theory, in addition to curvature, a geometric property of spacetime called torsion is introduced. And when there is torsion, a well-defined geometric quantity that can be calculated and so on, we see that this no longer occurs. Singularities are eliminated. In other words, there is a kind of leap and torsion at a certain moment in space. During gravitational collapse, for example, overrides the attractive force of gravity and produces something repulsive. So this removes singularities. Today we have good reason to believe that as soon as we incorporate quantum physics, quantum phenomena, into the relativistic framework, into general relativity, singularities disappear. They are eliminated.
Just to confirm for our listeners, and for myself as well, just to be sure, when we talk about a singularity, we're referring to the formation of a black hole from a star that destroys itself. That's what creates a black hole, right? And the idea is that either this can come from stars, or if we eliminate these singularities, it means that black holes could potentially be formed in a different way, not as a result of a star collapsing in on itself.
You're right to ask this question because it's a common misconception to associate black holes with singularities. It's true that initially there was a tendency to associate those two. At first, and throughout the history of general relativity, there was strong resistance to the idea of gravitational collapse leading to the formation of black holes, because if you extrapolate, you end up with a singularity. Physicists didn't accept singularities, and so for decades black holes seemed implausible, because black holes were equated with singularities. However, in reality, and I can honestly say this, even today we still don't know what happens inside them. We can throw around our equations, but as they currently stand, they are not perfect. They're imperfect because we don't yet have a solid theory of quantum gravity, and we can either imagine that there really is a singularity in there, or rather that there are other phenomena, quantum jumps, and so on. So, to repeat, today, to form a black hole, all you need is to compress a certain amount of mass, matter, and energy into a given volume of space-time. You then define an event horizon, a kind of gravitational trap. That is the black hole, and we don't know what lies at its core. It could be a singularity, a non-singularity, a wormhole, anything. All these strange things are theoretically possible, but a black hole is the event horizon.
Thank you very much for the clarification.
Very good. We talked a little about this. You mentioned a star passing near a black hole and what happens to it. We don't know what happens to matter when it falls into a black hole, whether it's matter or information. But what do you think actually happens to the information that falls into a black hole? Is it lost immediately? Is it stored somewhere? Can it be recovered? And maybe you could also explain what information means in this context. What exactly does that term refer to?
So, we've now come to a pivotal episode in the history of black hole theory, centered around what became known as the information paradox. It originally stemmed from a fundamental law governing the evolution of black holes, at first proposed as a hypothesis, but later proven. It was first formulated in a rather picturesque way by John Archibald Wheeler, who famously said, "A black hole has no hair." It means that during the formation of a black hole, nearly all the information about the matter that contributed to its creation is lost. Typically, billions and billions of bits of information. Things like shape, composition, and a whole range of other properties are swallowed up by the black hole, and only three quantities remain. Its mass, what's called the angular momentum, which is related to the black hole's rotation, and possibly its total electric charge. So the idea that a black hole has no hair meant that once a black hole has formed and reached equilibrium, meaning it's no longer interacting with anything, it is completely defined and fully described by just three parameters. Paradoxically, that made it the simplest object in physics. Let's take something simple, say a lump of sugar. If you wanted to describe it in full detail, you'd need billions of parameters. Sugar can be white, it can be brown, it can be cube-shaped. It has a specific form, it has an atomic composition, and so on. That's billions of parameters. And yet here you have an object, a black hole, that's described with just three parameters. Then in reality, we come to understand that while electric charge may theoretically exist, but in practice, it doesn't. In other words, when a black hole forms, it is electrically neutral. This means that the typical black hole in the universe is described by the Kerr solution, also known as a rotating black hole characterized by two parameters, mass and angular momentum. In other words, the black hole has absorbed an enormous amount of information. Well, that's good. It means that all configurations of matter outside the black hole have been absorbed by it. Thus, a classical black hole is essentially an information trap. This was the concept in the early 1970s, a trap for information. At the same time, black hole theorists like Wheeler, Hawking, Brandon Carter, and others were studying the laws of black hole evolution, purely theoretical at that point, since it was all just theory. They examined how black holes evolve, how they interact when influenced by one another, and so on. They also considered how an isolated black hole evolves over time, and they began to refine what was then called the laws of black hole thermodynamics. Why? Because there are four laws that govern the dynamics and evolution of black holes, which can be compared to the ordinary laws of thermodynamics. The most intriguing of these is the second law of thermodynamics, the well-known principle stating that in any isolated system, a specific thermodynamic quantity called entropy can only increase over time. So, what is entropy? It's a measure of disorder. In other words, it's a measure of the information we've lost about a system. The second law of thermodynamics tells us that in an isolated system, unlike, for example, a living system that constantly interacts with its environment, entropy increases over time. In other words, The system's usable energy decreases, and we're left with less and less information about it. Then the quantum field theorists entered the scene. And this takes us into the 1990s when they say, wait a moment, there's a problem here. You see, in quantum physics, information cannot be lost. There's a principle called the unitarity theorem. The name doesn't matter much. But what it tells us is that information must be preserved. So if we could describe black holes in a fully consistent way within the framework of quantum physics, then all information should, in principle, be recoverable. So that's when the debate began, and it became known as the information paradox. At first, two opposing schools of thought emerged. On one side, there were the relativists, around Hawking, Gibbons, and others, who argued that there was indeed an information trap, with some information irretrievably lost. On the other side were the quantum physicists, who insisted that something was wrong with that idea, that the paradox still hadn't been resolved. Over time, consensus has gradually shifted toward the view that quantum field theory is probably correct. Even Hawking eventually changed his stance and sought to understand how the information paradox might be resolved. The paradox still exists today. Many attempts have been made to solve it, often involving various approaches rooted in possible scenarios of quantum gravity. For example, there's a very interesting idea known as the holographic principle. The notion that the information associated with a black hole isn't actually stored in its volume, but rather on its surface. And indeed, there were some theoretical demonstrations, at least in certain specific cases, that showed it was possible to recover the formula for black hole entropy, the one given by Bekenstein and Stephen Hawking, by dividing the surface. Purely theoretically, dividing the surface of a black hole into very small units of area, microscopic ones, which are linked to what's called the Planck length. And then we count these units as bits of information. Here we return to information theory, and we recover the global entropy by counting the number of these bits. So, this idea that information is stored on the surface was quite interesting. A more promising idea comes from one of the theories of quantum gravity called loop quantum gravity. This theory was initially proposed by Ashtekar and later mainly developed by my colleague Carlo Rovelli, as well as Lee Smolin and a few others. It's a completely different approach from string theory, which I'm not really going to talk about here. The idea behind loop quantum gravity is to discretize space and time entirely. In other words, if you want to quantize gravity, that is, to make it discrete, then, since in general relativity gravity is geometry, what you're essentially doing is quantizing geometry. So instead of working with continuous spacetime, as is still done in string theory, for example, where you even have to add extra spatial dimensions, in loop quantum gravity we continue to work with three-dimensional space and time, but instead of being continuous, space-time is discretized. So there is the equivalent of elementary grains of space and possibly also of elementary grains of time, the equivalent of atoms of space and atoms of time. In this kind of framework, singularities are already eliminated because, for example, during gravitational collapse, there comes a point where we hit the elementary grain of space, which is not infinitely small, it is very small, but not infinitely so, and therefore there will be a bounce. Recently, Carlo Rovelli and some of his colleagues proposed an interesting theoretical idea, which I personally find quite compelling. Of course, it is what it is, and for now the idea can't be tested experimentally, but the proposal is to replace the concept of a black hole with what they call a Planck star. So what does that mean? It means we describe gravitational collapse, the usual process that forms a black hole, but now within the framework of loop quantum gravity. And so indeed, before reaching a singularity, which is impossible in the context of this theory. There's a kind of bounce at the scale of what's called the Planck length. That's why they named these objects Planck stars. And this bounce could actually eject matter and energy from the event horizon, producing what's known as a kind of white hole, appearing at the same location where the black hole originally formed. But because of extreme time dilation factors in our own universe, we wouldn't be able to observe it, even if it had already happened. Yet this would solve the information paradox, since nothing remains permanently trapped behind the event horizon if it eventually comes back out. So it's one possible way of resolving the information paradox.
So once again, just trying to simplify as best I can to understand, we start with the idea of a black hole as something where things fall in, like a well or a siphon, where information gets destroyed inside. But then we move toward understanding that, yes, black hole destroys information, but then expels that information back outside.
Well, actually, we can't say that a black hole destroys information. It imprisons it. It doesn't destroy information precisely. And quantum physicists say if a black hole evaporates, for instance, then since information isn't destroyed, in theory, we should be able to recover all of it.
Right.
Even in a different context from black holes, we often use popular science analogies to illustrate this quantum physics principle that information cannot be lost, what we call unitarity. They'll use the example of a piece of paper. You write a whole text, then you burn it. Completely turn it to ash. Quantum theory says, sure, you've broken it down into atoms and molecules, but the information is still there. And in theory, there could exist a process, currently far beyond our technological capabilities, that would allow us to retrieve that information entirely. It would be the same with black holes. They wouldn't have destroyed the information. They would have imprisoned it for a certain time, and eventually it would be recovered. Today, we believe that information is not destroyed inside a black hole. That said, I should also mention another hypothesis because, as I've said, we still don't really know what happens inside a black hole. There probably isn't a singularity, but there could be, as you know, even stranger phenomena, such as so-called wormholes. These are theoretical distortions of space that could allow some of the matter and energy entering a black hole to re-emerge elsewhere in the universe, having passed through the wormhole. By the way, I'll just mention that my next book, which is about to be published, is precisely titled Traveling Through a Black Hole with Interstellar. In it, I decode all the scenes from the film Interstellar, especially the final, somewhat mysterious ones where no one understands anything except the astronaut. And the movie also features wormholes, though in that case, they're artificial. So I dedicate a whole chapter to discussing the status of wormholes, which often spark the imagination because people think, one day, if we have traversable wormholes, we could finally leave our solar system, visit other stars, even leave the galaxy by using these shortcuts through space-time. They'd let us undertake journeys that are totally impossible on human timescales, without ever violating the local laws of relativity, which of course prevent anything from exceeding the speed of light locally. By taking such a shortcut, we could end up in a distant galaxy in a week. So naturally, it's something totally fascinating for science fiction fans, for anyone who dreams of such things, etc.
Thank you very much, Mr. Luminet. In an article titled Big Bang, Cosmology and Religious Thoughts, you reflect on Friedman's idea of the universe being created from nothing. And there's the quote I'd like to cite. Nevertheless, metaphysical anthropological ideas can play an important role inside the science research process as an epistemological tool, helping to clarify the use of some fundamental notions. In your view, how can theological ideas help in addressing the mystery of black holes? Do you think a black hole might be a kind of absolute nothingness?
I believe you're quoting an excerpt from my book that came out last year, titled The Big Bang Revolutionary, in which I trace the highly complex and fascinating history of how the models of modern relativistic cosmology were developed and all the obstacles that gradually arose against this truth. This complete shift in the scientific paradigm. Why a complete shift? Because before the first dynamic cosmological models, those by Friedman, which were later further developed especially by Georges Lemaitre, people thought the universe simply couldn't have a beginning. It was considered almost a physical scandal to even imagine that the universe might have a beginning. And so this marked a real departure from any possible theological account of Genesis or similar narratives, of course. And when Friedman first discovered the cosmological solutions to the equations of general relativity that involved a beginning, which he called creation of the world ex nihilo, he made a connection afterward. Not with Christian theology, though, because he was more drawn to Eastern cosmogonies. He connected it to certain origin myths from India and surrounding regions, while still being very cautious, of course, about the metaphysical implications. So he rediscovered all of Friedman's results and developed them further. He went much farther than Friedman and formulated what was first called the primeval atom model, which later became known as the Big Bang model. And that means it is a model of the universe in expansion, but with a beginning to that expansion at a finite moment in the past. Lemaitre was a man of religion, and he was unfairly accused of what's called concordism, trying to align a scientific narrative, meaning cosmological solutions from general relativity, with a potential theological account of the world's creation. I think theology and science shouldn't be mixed, but they shouldn't be completely separated either. And that's why the quote you gave earlier says that theology doesn't directly contribute to scientific development, but it does help us reflect on the foundations of scientific reasoning. Because at the end of the day, no matter what we say, even the most rational scientists, even those who declare themselves materialists, and not all of them truly are, they still carry in one way or another a kind of background, a cultural, philosophical, metaphysical background. And this background, even if it's not always conscious, influences the directions we take in our research. So it's not irrelevant. In fact, it's quite valuable to recognize that there are some theological considerations floating around. Actually, it's quite interesting that we're discussing this now, because it just so happens that my next book, which I'm currently working on, I'm very active at the moment, is scheduled to come out in 2026. It's going to be a massive anthology on cosmogonies. The title will be The Origins of the Universe. So I've gathered all the major texts from the history of humanity that deal with the origin of the world, or worlds. It goes from philosophical texts to theological narratives and then on to modern scientific accounts.
Very well. Perfect. Thank you very much for that additional information. It really helps us understand the kind of impact one can have in this field, or in science in general. Now, shifting topics a little, come back to something you briefly mentioned earlier, and you said we'd return to it. Let's talk about black holes at different scales.
Yes, it's important to bring this up.
Exactly. So I wanted to ask, what is the fundamental difference between supermassive black holes at the centers of galaxies and stellar black holes? Do they differ in their acceleration dynamics or in the way accretion disks form?
Sure, but before answering that specific point, I'd like to mention that theoretically we distinguish at least 5 different scales, 5 types of black holes, based on their mass. Out of these 5, 3 are more or less observed today in astrophysics, while the other 2 remain purely theoretical. Now, among the ones that are observable, there are 3 astrophysical categories. First, we have stellar mass black holes, then what we might call intermediate mass black holes, and finally, massive and supermassive black holes. So these are essentially mass scales, but what makes them truly different is that they don't form in the same way. Their formation mechanisms are fundamentally different. Very briefly, stellar black holes are formed from the gravitational collapse of massive stars. Stars can't have arbitrary masses, so stellar black holes have a minimum mass about 2.5 times that of the Sun, and a maximum mass of around 100 times the Sun's mass. simply because they form from the collapse of stellar cores. Now, intermediate mass black holes are thought to lie between a few hundred and up to 100,000 or even a million solar masses. The idea of their existence was proposed about 30 years ago, but only recently have a few rare candidates been identified, although the processes by which they form are still not entirely clear. Then we get to the next scale, massive black holes. These begin at around 1 million times the mass of the Sun. A good example is the supermassive black hole at the center of our galaxy, which weighs in at 4 million solar masses. And beyond that, we have supermassive or even ultra-massive black holes, and the real giants of the universe. These can reach several billion times the mass of the Sun. This is exactly the kind of black hole found in the galaxy Messier 87, M87, which was the subject of the first ever direct image of a black hole. The mass of this black hole is 6 billion times greater than the mass of the Sun. In recent years, as we've observed more and more distant galaxies, we have not, of course, observed black holes directly, but we have seen extremely energetic phenomena in distant galaxies, so intense that they can only be explained by the release of gravitational energy from black holes. From this, we've been able to estimate their mass. Now we know of supermassive black holes whose mass exceeds 10 billion times the mass of the Sun. In fact, the largest known black hole to date lies at the center of a distant galaxy called TON 618, with a mind-boggling mass of 65 billion suns. These are astronomical numbers, and they might seem abstract to most people. But it helps to remember that the size of a black hole is directly proportional to its mass. For example, a stellar black hole with 10 solar masses would have a diameter of about 30 kilometers. A black hole of 10 million solar masses, that would be 30 million kilometers across. And the one with 10 billion solar masses would span 30 billion kilometers. So the diameter of the TON 618 black hole is estimated at around 180 billion kilometers. You could fit our entire solar system inside it. That is, these supermassive black holes are truly incredible monsters out in space. So, all black holes, regardless of their scale, would share similar properties in terms of distorting space and time. But as I mentioned earlier, for instance, when it comes to tidal effects, these are only significant for moderately massive black holes. From stellar mass black holes, where tidal effects are extremely strong, up to massive black holes of about 100 million solar masses. Beyond that, for even larger black holes, the tidal effects occur entirely inside the black hole. But take stellar mass black holes, for example. If we go back to dreaming about science fiction, space travel, and approaching a black hole, it's actually not possible to get close to a stellar black hole. That's because tidal forces start acting at such large distances that we encounter a phenomenon called spaghettification. In other words, as soon as one comes close enough to a stellar black hole, the tidal forces begin to act at such a distance that they stretch and elongate any object along one direction into what we call a spaghetti. So any structure, any configuration, would be completely torn apart long before reaching the event horizon of a stellar black hole. There's also a topic we haven't yet discussed, but I'll mention it briefly. It's bound to play an increasingly central role in all these studies, and that's the detection of gravitational waves. It is through gravitational waves that we now have access to certain properties of black holes that we cannot observe in the electromagnetic spectrum, because of course there's no light. Today we already have a catalog of well over 100 gravitational wave events involving either the merger of stellar mass black holes or the merger of neutron stars, or so-called hybrid mergers between a black hole and a neutron star. And in all these cases, we're learning extraordinary things. For example, one of the key takeaways is that the masses of black holes involved in gravitational processes turn out to be somewhat larger than the ranges we previously had based on so-called electromagnetic black holes. These were black holes detected in binary star systems, called X-ray binaries. You have a black hole paired with a gaseous star, pulling gas from its companion star, forming an accretion disk that emits X-rays, from which we estimate the mass. Now, with gravitational wave detection, we found some of the smallest black holes, right near the minimum mass limit, as well as stellar black holes that are much more massive than we had previously thought. In particular, some gravitational wave events have involved cognate black holes of 60 or even 80 times the mass of the Sun, whose merger resulted in a final black hole of 140 solar masses. Therefore, the question arose, are there more black hole mergers than we initially believed? When the first black hole merger was detected in 2015, we thought it was a stroke of luck. But then we kept detecting more and we began to wonder, maybe many more black hole mergers occurred in the early universe than we had imagined. And if so, if there were a large number of massive stellar black hole mergers early on, it could also help explain the existence of intermediate mass black holes and the other related phenomena. Some have even gone so far as to suggest, though I personally think that's a bit too speculative, that there might have been so many of them that it could explain a portion of dark matter. But I don't think so. The missing quantities of dark matter are so enormous that black holes can only contribute a very small fraction to that.
That's exactly what we wanted to talk about. It's truly astonishing what modern technology allows us to do, how we can now see farther and examine things that are increasingly small. There was a very interesting article published in September 2020. For those who haven't read it, the article is titled, "The Mysteries of Dark Matter." In that piece, you state that dark matter is primarily non-baryonic in nature, even though it produces gravitational effects similar to those associated with ordinary mass. That's a fascinating idea. So here's my question. Do you think the immense gravity and the distortion of space-time near a black hole could be caused, at least in part, by the influence of non-baryonic matter? And could there be a possible connection between dark matter and black holes?
So, to briefly summarize, the issue with dark matter is as follows. The matter we can see, luminous matter, is by definition atomic in nature. Technically, we refer to it as baryonic matter. We now know that this baryonic matter accounts for only an extraordinarily small fraction, roughly 1%, of the total mass energy content of the universe. So clearly something is missing. In the absence of better terminology, we've come to call this missing component dark matter, simply because we cannot observe it directly. So the first step was to say, what is dark matter? Well, maybe it's just ordinary matter, atomic matter, that is baryonic matter, the same kind of matter that makes up planets, stars, galaxies, and ourselves. And it's not unreasonable to think there might be configurations of baryonic objects too small or too faint to emit light, like failed stars or other compact objects. That's the basic idea. However, we are faced with constraints from what's known as primordial nucleosynthesis in cosmology, the process that formed light elements in the early universe. These constraints effectively rule out the possibility that all dark matter is baryonic in nature. In fact, what we consider normal atomic matter, which we once assumed was dominant, turns out to be marginal. In fact, it's rather even that, so that atomic matter represents at best only about 5% of the total. And that's not enough to explain the gravitational behavior of the luminous matter. So this means that there is a form of non-baryonic dark matter that acts through gravity, since every form of normal matter does indeed create gravity. And so, this is what we generally refer to as dark matter in the broad sense, and it would represent approximately a quarter of the total mass energy content of the universe. In fact, a simpler and more plausible explanation, in my view, is that the hypothetical dark matter particles have properties that make them extremely weakly interactive with ordinary matter. They would behave a bit like neutrinos, which are not a form of dark matter, because neutrinos interact only very weakly with our detectors. And yet we still manage to detect an infinitesimal handful of the vast numbers that pass through the detectors. The proposed non-baryonic dark matter particles, known as WIMPs, weakly interactive massive particles, would interact even less than neutrinos. So we can still say that we haven't yet succeeded in building detectors sensitive enough to register dark matter particles arriving from the cosmos, even though we've certainly tried. Now, the existence of non-atomic particles, whether dark or not, is perfectly natural since we create them artificially in the laboratory. In particle accelerators, when we collide protons, which are baryonic particles, we produce cascades of new particles that are no longer baryonic, carrying away part of the energy and mass. So we imagine that the hot early universe functioned as a kind of superparticle accelerator, capable of producing a profusion of massive, stable, non-baryonic particles which could now account for the gravitational behavior of luminous matter. The question remains highly debated. The prevailing consensus is that dark matter likely exists, but we haven't detected it yet. Nevertheless, many researchers are exploring alternative models, modifying, for example, the laws of gravity, in an effort to explain cosmic dynamics without invoking this form of dark matter.
Very good. Perfect. Once again, this brings us quite naturally to our final segment. These hypotheses, the way science evolves, and it leads us to the last part of our discussion, the future of black hole research. So my question would be this: what are, or perhaps to simplify the question even further, what is the one area that currently captures your attention the most in terms of what still needs to be done in the future? What, in your view, is the future of black hole science? Is there a particular field that especially draws your interest?
Well, if we focus strictly on black holes, though as I mentioned earlier, black holes sit at the intersection of several different theories and have far-reaching implications for fundamental physics, then we can imagine two broad areas of future progress: theoretical advances and observational or experimental developments. On the theoretical side, what we might hope for is the development of quantum gravity models, or something else, that can plausibly resolve the information paradox and ideally eliminate the singularities as well. That would be a major breakthrough. But of course, there's no guarantee that such progress will happen. On the observational side, however, we can be much more confident. Technological developments are progressing at a truly remarkable pace, and we can expect that they will continue to enhance our ability to detect more and more black holes. And then there's another important aspect, that's gravitational waves. I'll say it again, this might be the newest and most fascinating window we've opened. Gravitational waves grant us access to a part of the universe that emits no electromagnetic radiation, no neutrinos, only gravitational waves. Thanks to them, we're beginning to observe phenomena like black hole mergers, which until recently were purely theoretical and completely inaccessible. It's an entirely new observational window, the gravitational window. And what's remarkable is that it enables us to make predictions with extraordinary precision, far exceeding the accuracy of electromagnetic observations. Gravitational waves grant us access to a part of the universe that emits no electromagnetic radiation, no neutrinos, only gravitational waves. Thanks to them, we're beginning to observe phenomena like black hole mergers, which until recently were purely theoretical and completely inaccessible. It's an entirely new observational window, the gravitational window. And what's remarkable is that it enables us to make predictions with extraordinary precision, far exceeding the accuracy of electromagnetic observations. The project currently underway, it's financed, it's fully budgeted, is called LISA. It's a space-based gravitational wave detector. And instead of a terrestrial baseline of just a few thousand kilometers, we'll have a baseline of several million kilometers in space. So there's an absolutely exciting future ahead of us, especially when it comes to understanding these extraordinary and fascinating objects that are black holes of all scales, from microscopic to supermassive.
Thank you so much. What advantages, in your view, would humanity gain from a deeper understanding of the true nature of black holes?
That really ties into the broader question. What's the point of doing fundamental science? I'm not talking about applied science with immediate practical outcomes because clearly understanding black holes isn't going to change our everyday lives or lead to direct applications. But delving ever deeper into the nature of reality, which, I repeat, will probably always remain partly inaccessible to us, there will always be a final veil hidden behind, still brings our maps ever closer to the actual territory as we make progress. And it is always an extraordinary benefit to deepen our most profound vision of the universe.
You're a truly talented person. We've heard all about your achievements. Beyond books, articles, and research, you also create music. Could you tell us, in your opinion, what does space sound like?
Yes, strictly speaking, as you know, there is no such thing as sound propagated by acoustic waves in space. Sound is acoustic by nature. It requires a medium. But space is either far too empty or too tenuous a medium for acoustic waves to travel through. What we do receive are electromagnetic waves, which can be converted into acoustic waves. For example, the radio waves captured by large antennas of radio telescopes are transformed into an electric signal that varies over time. It's a bit like how the needle of an old vinyl record produces an electric signal, which is then converted into sound by speakers. And this, I must say, is something truly wonderful. Something I've had the good fortune to work on myself. It's actually the capture of electromagnetic signals from what we call pulsars, which are remnants of supernova explosions. These are very compact stars, neutron stars, that rotate rapidly on themselves, emitting a radiative beam somewhat like a lighthouse, with metronome-like regularity. Because the rotation speed of neutron stars is extremely, extremely stable. When we perform this transposition, that is, when we capture the pulsar's radio signal, convert it into an electric signal, amplify it, and connect it to a speaker, we can actually hear the rhythm of the star's rotation. And it sounds like percussion, a kind of natural human percussion system. That's how I had the chance to take part in the creation of the first astronomical and musical composition called Le Noir de l'Étoile, together with the great composer Gérard Griset, founder of an important movement called spectral music. He had heard recordings of these sounds at the University of Berkeley thanks to some astronomer colleagues, and upon returning to France, he contacted me to collaborate on the creation, to incorporate these rhythms into a musical composition. So yes, I had the great fortune to be part of that. And afterward, I had many other collaborations. In fact, I recently wrote an entire book about it, titled Du piano aux étoiles, From the Piano to the Stars, where I recount my personal musical journey.
Thank you so much for your time and for your detailed answers to our questions. I hope you also found our questions interesting. We tried to cover a variety of topics.
Yes, very much so.
Well then, thank you again. Have a wonderful rest of your day and see you very soon.
Goodbye. Thank you very much.